This episode documents the database and data underneath the simulation. I'll cover how the database was built and what else you can use it for, like the graphic shown here. The database was designed to be simple and robust enough to support future expansion of the simulation. I try to conform to modern database design principles, but I'm not fanatic about it. First, I searched the internet to see what data were available. For the model I had in mind, some of the data elements were not immediately available. I would need to change the model, make some assumptions, or develop surrogate data from other sources. Nevertheless, the form of that future data does affect the design of the database and its tables. The table structure needs to be robust enough to handle data that I don't have yet. I chose to use the same primary key that Berkeley uses, though I use a far different format. My approach is not the same a database purist would use, but I have reasons for that. Formatting and importing the data is rather mechanical. Quality control is not. The most convenient data is available in Microsoft Access files at Berkeley. These need some work, which I'll cover next. The fission yield data started at Berkeley, but the Brookhaven data was more conveniently formatted, and it turns out more accurate. The Tori2 database has a strangely named table with most of the branching data. However, it lacks data on decays that end in metastable states. The International Atomic Energy Agency has data on that, unfortunately packaged in a locked PDF file. Also, Brookhaven maintains the excellent NuDat2 website. This isn't suitable for downloading masses of data, but for quality control on individual isotopes, it is very friendly. The Tori2 database MDB file from Lawrence Livermore Lab can be loaded directly into Access. I don't need all of it, and it doesn't have all the data I need. The Tori2 isotope characteristics table, including half-life, is called Parents. I renamed it Isotopes. The Parents2 table describes the decay modes and branching ratios for each isotope. I renamed that Daughters. The initial fission yield data, which includes several fuels and neutron energy levels, is from Brookhaven. The Tori2 data has some flaws from my perspective. The sums of the branching ratios do not always equal 100%, especially when neutron emission is involved. Physicists probably have a reason for that, but it is inconvenient for me. There is also some redundancy, which is not as big a problem as with other databases. The problem is worse if the data changes a lot, but atomic numbers or element names are not likely to change. The biggest change was in the primary key for the database. Tori2 uses a cryptic integer that multiplies the proton number by 10,000, adds the atomic weight, then adds 300 for each metastable state number. It is hard to work with, but it is unique. The primary key has to be unique, but someone forgot that isotope names, by themselves, are unique. I'll be using the far more readable isotope names as my primary key. Names will consist of the atomic weight, a dash, and the element symbol. If necessary, this will be followed by another dash, and an M and an integer to indicate the metastable state. The working data resides in 3 tables. The isotopes table will also have fields for the neutron absorption and fission cross-sections, eventually. Other characteristics that depend only on the isotope might be added. The Daughters table will eventually hold decay energies, which depend on the isotope and decay mode. The Yields table currently has 5 fuels and 3 neutron energy levels. There is also an Elements table. You need that when you want to determine the number of protons, which is not part of the isotope's name. That and the other parsed elements of the isotope name are available in the standard view. This is the source of the pretty stacked bar chart on the title slide. It's named the Nepal view for a professor I once had who said he never saw a stacked bar chart that he liked. Before loading the data into these tables, let's look at the user input tables. The user will select the fuel mix and reactor characteristics before each simulation run. These choices will be saved in their own tables by name. The 9th tar sands test run has 8% enriched uranium for fuel and 92% 238 uranium for non-proliferation purposes. The 238 uranium will fission if hit by a fast neutron, so for some reactors it is fuel. One example of a reactor design is the denatured molten salt reactor. This is a thermal design, so most of the neutrons have been slowed down by its graphite moderator. The percentages here are notional and assume that fast neutrons cause at least a small number of fissions. The percentages come from a more detailed simulation of the core and its neutron histories. Ideally, the neutron energy distributions and future cross-section data will be aggregated to match the energies available in the fission yields table. However, at first they might just be generic values for the purpose of a political narrative. Any salt cleaning process will have a name and specify that a given isotope will be reduced by some percentage starting at a certain time. The reduced percentage will be carried forward on the assumption that the cleaning gear is never turned off. In the future, the model might be enhanced by changing the fuel or the salt mix on a schedule. For instance, we might run dirty used fuel for half the reactor's life, then switch to the cleanest fuel, 233 uranium. For the table that stores the simulation output, we go back to the original question: what's in the salt? That question has evolved, and the answer now depends on reactor design and operation. The final output table will store about 30,000 records for each simulation run. That's a history of the evolution of about 1,000 isotopes over 30 time steps. The results can be used for that political narrative I mentioned earlier. Here is part of a presentation that compares nuclear choices. The simulation should provide the numbers for the blue boxes. These include how much fuel is consumed, in tons per gigawatt. For some reactors, some of that will be from current stockpiles of spent nuclear fuel. The original focus of the simulation was waste products, and that can be as detailed as we wish. The work required to obtain such output includes quality control. My weapon of choice is Excel. First, let's export the data into Excel, make a pivot table, then create a pivot chart from that. For the first QC graphic, I'll recreate the pretty chart from the title page. The field list for the pretty chart is shown here, as the YouTube window is too small. The NEPL query provides some 15,000 records, which become 15,000 rows in the new NEPL worksheet. I've turned on some filters to look only at the decay chain for atomic weight 66, specifically for 233 uranium as the fuel, in the thermal region. The bottom record has a yield of 0. Unfortunately, the raw data does not include such records. I had to add them to fill the gap and complete the decay chain. That quality control task is not yet finished. Here is the pivot table created from those 15,000 records. I've already set up the field list to match the last slide, and I used the report filters to focus on 233 uranium thermal again. The numbers in the highlighted row should match the 66 chain numbers we just saw. I also created the raw pretty chart, then made it prettier, and took a picture of it. The most popular element is tellurium, the broad orange swath on the right. I do agree with Dr. Neppel that a stacked bar chart can hide things. The various isotopes of tellurium in another chart would show a bell-shaped curve, which is disguised here by the stuff under it. That is easily fixed. Back in PowerPoint with the large print version of the field list for the next set of charts. This slide also shows some results. On the left is silver with fast neutrons. The bell shape of a normal distribution is apparent. On the right is a possible outlier in the cadmium data. Back in Excel, here's the first of the isotope distribution charts. It's silver again, but in the slow spectrum. We can change that to match the previous slide. I'll select the 14 million electron volt fast neutron data. We can also change the element to cadmium and see an outlier. We'll want Brookhaven to confirm or alter the number that causes that peak. There are about 50 elements in this data set, and usually 3 energy levels, so I have some 150 charts like this. Here's silver at low and medium neutron energy levels. Here's the distribution of silver isotopes produced by a fast neutron, as seen on the previous slide. It's better behaved than the rather ragged low energy level chart. A little variation is not a problem. We can scroll through these looking for more outliers or other trends. That's the first rule of data mining. Just look at the data graphically. Excel pivot charts are great for that. Here's a possible gallium outlier. And for gadolinium, why does plutonium produce so much more of that element than uranium does? Among the fast neutron distributions, there is a subtle anomaly. There are only 4 curves on the right. We seem to be missing fast data for 241 plutonium. Let's do one last bit of data mining on that. We won't need that chart anymore, and make a couple of arrangements on the field list, make a little matrix, and fix that filter. In this little matrix, we see a gap for 238 uranium in the slow speed neutrons. That's alright because low energy neutrons don't affect 238 uranium. We also see some data that we don't need for plutonium-239 in the medium fast range. We still have a gap in the 241 plutonium at high energy. This matrix sums all the yields. All of these sum to 2, since 2 smaller nuclei are created every time a fuel atom is split. This is a quality control check by itself, but a simple count is also useful. Changing the data statistic, the records are now counted, not summed. So there are about 1,000 rows of data for each combination of energy and fuel, except for the 241 plutonium at 14 million electron volts. I haven't loaded the fission yield data for americium and curium yet, but a look at the raw data shows the same gap. This is a problem. Overall, the project is doing well in the area of database design, and much data has been imported. But we have identified 3 problems: the lack of fast data for the heavier actinides, some outliers in the current data, and gaps where the decay chains aren't complete. It may be a while before I publish this database.